Good afternoon, everyone. Good morning, some of you folks out there. Brett Zerba, commercial and training engineer with Taco Comfort Solutions. Taco, actually Taco Inc. Who knows what the name is today? Anyways, welcome to Taco Tuesday, commercial focused, and you can see with the first screen up there what it's on, balancing. Very interesting topic, proportional balancing. Oh boy, it's even more than I expected. There is a handout that's available. It's some of the slides, or if not all the slides, or maybe extra slides, but there is a handout available, PDF. 24 hours after today, you'll get a link to the recording. So we are recording this webinar and access to your PDH certificate if you'd like to print it out. If you ever have issues with that, let us know. Some of you have been through these before, not everybody, but Taco is a 105-year-old privately held company worldwide now. We've really expanded in the past 5 to 7 years. We have offices in Europe, Italy, and Czech Republic, and Poland. We have a foundry in Vietnam. We've been in Canada for over 90 years. We are quite we just opened up 2 new facilities, one in Fresno, California, and one in Lubbock, Texas, for our vertical turbine pumps. So really, it's amazing how much we've grown. Currently, the present owner is Johnny White. He's the 3rd generation of the White family that owns it. And Cheryl Merchant is the current global CEO that runs everything on a day-to-day basis. It's quite the company. We are headquartered in Cranston, Rhode Island. And I noticed some of the names on the list here that have been to Cranston, Rhode Island. Matter of fact, I won't say his last name, but one was just here, I think, last week or the week before. My friend Joe from the Carolinas. I think he's still from the Carolinas. Anyways, good seeing some folks on the name. Today's presenter. Oh, good. I should have asked if people could. Hi, Joe. If could hear me, but it's based on Joe responding, I think he can. So listen. Normally, it's either Rich or I that are presenting, but today we have Tony First, one of the newer trainers at Taco. It's amazing that our company continues to invest heavily in training, and obviously a lot for the industry, but a lot of other training as well. It's pretty phenomenal what we go through. I don't want to take up too much time on that, but we are very pleased to have Tony on board. And Tony's going to put on today's presentation. I will be moderating it and monitoring the questions. So at this point, Tony, I'm going to turn it over to you and take it away, my good friend.
Thanks, Brett. Good afternoon, everybody. Hopefully everybody's having a good day, and we'll get started talking about proportional balancing. And so some of the things we're going to talk about today, we're going to talk about what is balancing. We're going to talk about fluid control methodology and the different ways you can balance a system. We're going to talk about the energy implications, because each balancing method has a direct impact on the energy consumption of the system. We're also going to talk about code compliance, because whether you know it or not, balancing is actually required by the code. And then at the very end, we're going to talk about the process of proportional balancing and what it is and how you get through it. So why do we balance? Well, it's all about energy and comfort, and understanding it's a balancing act in a lot of ways, because we've got to look at balancing the system, but we also got to balance the cost associated with what type of balancing methodology we're going to use, and as well as maintaining system efficiency, system sustainability, and overall pressure drop in the system. So what we really have to understand is all of these things add up together, and if it's not done correctly, we end up with wasting energy. And wasted energy means that our customers, our building owners, are spending more to heat and cool their building than what they really need to. And our goal as engineers is to help reduce that energy consumption. So when we look at this, some of the benefits of balancing, okay, first of all is comfort, maintaining the building comfort. And by doing that, we're meeting the design intent. Now, part of this is also to reduce startup time, so we get the system up and running and fully commissioned and fully operational per the design intent quickly and easily, okay? One of the other key components of hydronic balancing is error detection. If there's a problem in the system, not necessarily a design problem, but it could be. But what about an installation problem? Somebody's installed the piping wrong. Somebody's got a valve that's not open completely. Somebody's not gotten all the air bled out of a system. The balancing contractor, the test and balance contractor, can help identify those problems and fix them before the building owner gets into the building. By properly balancing a system, we also reduce the total pump energy. And reducing pump energy goes to meeting our sustainability goals, meeting our energy performance goals. Okay, so when we look at this, we look at a building, we look at the design intent of the building. And this is what we as engineers are all concerned about. So our design intent in this particular example, it's 5545 on the chilled water side. We've got a 250-ton chiller, we're moving 600 GPM, and we've got the right flows going out to all the different air handlers in the building, okay? And we're maintaining the right delta T's. This is the way we've designed the system, okay? So if we assume an outdoor air of 100 degrees and a 250-ton chiller and a 10-degree delta T and 600 GPM, this is what we intended. This is what we put on paper of what we intended to have happen and what we told the owner we were going to do. Well, what actually happens is, if I look at an unbalanced system, okay, I've still got the same 100-degree outdoor air, but now I've got incorrect flows throughout the building. And as I increase the flow rate through the chiller, what happens is I start to lose chilled water delta T. So instead of a 10-degree delta T, now I only have a 6-degree delta T. Now what that means is my 250-ton chiller is only capable of producing 197 tons, so I'm only getting 79% of the capacity out of that chiller. And because I'm not running that chiller at its design delta T and its design performance, its energy usage goes way up because I'm not producing the right number of tons of cooling. So this is part of the reason that we have to balance the system. We want to make sure that we distribute that water equally throughout the entire building. Okay, so once we come back to that balanced system, now the system delta T is where it's supposed to be. We're delivering the design tons, and everybody in the building is happy, and we're keeping the energy cost at their lowest possible value. So when we look at this, fat fingers here on the remote, what is really happening? Okay, so we've got to understand that even though in a hot water system, I may be moving 1 million BTUs, and in a chilled water system, I may be moving 1 million BTUs. My delta T's are different, and in my chilled water system, my flow is 6 times greater than what the hot water system flow is. So in chilled water systems, it's even more critical that we properly balance the system. And I'm not saying that we don't want to balance the hot water system, but the impact on the system performance is greater for a cooling system than it is for a heating system, just because of the fact that the flows are so much greater. So we have to understand that, and we have to understand that if that flow is incorrect in the cooling system, then we've got a bigger chance to offset, to create negative offset in our energy performance. So we've got to pay attention to that. And that's why this is really, really a critical component of every system design, is getting it properly balanced. So we use balance valves to balance the flow throughout the system. Now, yes, I can balance the system without the use of balance valves, okay? The problem is it takes a lot more time. So if I go to my coil, first thing I have to do is I have to determine what my airflow is through the coil. So I'm going to do a pitot tube traverse of the ductwork leaving the coil, and that may be an 18, 24, 36 point traverse. So I'm calculating velocity and turning that into volume. Then my delta T measurements across the coil on the air side. Then I'm going to take my delta T measurements on the water side across the coil, and I'm going to input them into the formula that's up on the screen. So I'm going to take the airflow times 1.08, which is a constant, times the delta T of the air side, divided by 500 times the delta T on the water side. Now, if you can imagine in a modern building, you've got 50, 60 air handlers in a building, And having to do this to every air handler and take those calculations, this is the reason the balance valves are so critical, because now it makes it easy to determine how much flow you're getting through each individual air handling unit or each individual coil. So if I have a balance valve, the thing I'm looking at is I'm looking at delta P across the balance valve. And every balance valve out there has a C sub V rating. And if I know what the C sub V rating is, I can calculate out what the pressure drop has to be at any flow rate, as long as I know what the C sub V is. That C sub V is a constant. It's known as the flow coefficient. And every valve out there has a listed flow coefficient. So if I know what the C sub V is, then I can calculate what the pressure drop is going to be. If I know what the pressure drop is, and know what the C sub V is, then I can calculate the flow. So by using any one of the three formulas that I've got on the screen, you can instantly figure out exactly what the flow rate is through a balance valve, regardless of that balance valve, as long as you know what that valve's rated C sub V is. It gets really easy. So the one time that I don't typically see balance valves is on reverse return systems. Now, reverse return systems by nature, the pressure drop through each individual device tends to be more equal if the reverse return is laid out correctly. The problem with reverse return systems is, one, they're expensive because you're running an entirely extra pipe the length of the building, and that creates some challenges because, as we all know, we don't have unlimited budgets when we design a building. As much as we would like to have an unlimited budget, it's just not practical. So reverse return, while they tend to self-balance, you still need balance valves because that's the one way you can measure the flow at each point. You may not have to do as many adjustments to them, but it's nice to have that balance valve so you know exactly what the flow rate is through each individual coil. Now, when it comes to balance valves, we have all kinds of choices, okay? And so it's really about understanding what each one does, how they work, and which one is the best one to apply for your system. So we've all heard about PICVs, which is a pressure independent characterized control valve. We have manual balance valves, and we have flow limiters. All three of them do the same thing. They all tend to balance the flow rates through the system by redistributing the pressure drop and keeping the pressure drop at any point in the system to be all the same. So that's what we're doing with a balance valve. And the thing everybody's got to understand is some are better than others. And I think once we get done today, you'll all have a better understanding of what really makes the most sense and what the code dictates that we do, okay? So first of all, when I look at a balancing valve, what is it? Well, it's a high precision throttling valve. Yes, I can take and put a ball valve in, and I can throttle the water flow with a ball valve. However, is it repeatable? Am I going to get the exact same measurement every time when I open or close that valve? And is the valve going to get returned to the exact right position? The other problem with using conventional ball valves is it doesn't have pressure ports. So I have no way of measuring the differential pressure across that valve. Now, yes, a ball valve or a gate valve or a globe valve does provide positive shutoff. However, one of the advantages with a balance valve is it has a memory setting feature, so that once I've set it, I can lock the memory stop, I can close the valve completely, and then open it back up to the memory stop, and I know that that valve is in exactly the same position it was before I closed it. So I can also use it as, as a positive shutoff valve, but it also has that added feature of the memory stop, so I can get it put back in the exact same spot every time. And what the balance valve is it's to divert or balance the flow of water throughout the entire system. So what are we doing when we proportional balance? What are we doing, and what's the whole idea here? So we look at this, it's about circuit balancing and balancing all the different circuits within an HVAC system. So It's about energy conservation. And the exact definition of circuit balancing is the practice of regulating system flow to ensure that design flow is available to every terminal unit under all conditions. So that's what we got to maintain. So if I look at ASHRAE 90.1, most of us in the US and Canada design to ASHRAE 90.1. Now you may be designing to different versions of it depending on what year your local code is adopted, but we're all designing to ASHRAE 90.1 in some form or fashion. So if I look at ASHRAE 90.1 and I look at 67331, it specifically says all HVAC systems shall be balanced. And it also goes on to say that there has to be a written balancing report if the conditioned space exceeds 5,000 square feet. Well, let's be realistic, folks. There's an awful lot of buildings that we design systems for that are bigger than 5,000 square feet. So by code, we have to balance the system and we have to have a written report documenting the balancing. Here's the part that most people don't know. Under 67333, hydronic systems shall be proportionately balanced in a manner to first minimize throttling losses. Now, the reason this is important is to understand the difference between PIC-Vs, manual balance valves, and flow limiters, okay? That's what we're going to talk about here a little bit. So if I look at, energy efficiency and I look at what is going on with my
Tony?
system. Yes, sir.
Tony, in regards to that 3333, how many threes there were, in layman's terms, that means you can't add false head to a system, or is that one of the definitions of that?
It means you can't add false head to the system, but there's 2 points in that statement to really understand it, is that systems have to be proportionally balanced and minimize throttling losses. And what that means is that ASHRAE 90.1 is all about reducing your total energy cost. And to do that, if I add flow limiters or other pressure regulating type devices to the system, automatic or manual, I'm increasing the pressure drop. And we'll talk about that here in a minute, Brett, and we talk about flow limiters and how flow limiters really work and what they do to your system overall.
10-4.
And manual balance valves don't have that problem, okay? So Those are the key points to understand there. So if I look at this, and if I look at an unbalanced system, and so let's say, I'm originally designed for a 10-degree delta T, and I'm not delivering that delta T. I'm delivering it at 7 degrees. So I'm operating at 190. I'm operating at 190 GPM over pumping. So I'm wasting pump energy. I'm also costing an additional $41,000 a year in energy cost. Here's the one that nobody takes into consideration. Okay, because of the excess velocity through the chiller tubes, I've decreased the chiller life by 4 years. I've decreased the life expectancy of that chiller, and it's going to cost the owner an additional $50,000 in lost life expectancy out of that chiller. So you're affecting the overall performance of the equipment, you're affecting its life expectancy. We design systems, we expect 25, 30-year life expectancy. We don't expect it to take 4 or 5 years off that life expectancy just because we didn't set this building up correctly. Okay, so when we look at balance valves, we know that we want to act as circuit isolation, flow regulation, flow measurement, and the goal is to maximize energy efficiency and make sure we're meeting the design intent. Okay, and we want to reduce the life cycle cost to the lowest possible value, but we don't want to negate the building. So if I look at manual balancing, manual balance valves have the lowest first cost. They are the least expensive balancing methodology that we can employ today. The nice thing is they are extremely flexible. Okay, I can readjust them as needed if the building usage changes. As much as we'd like to think that building usage stays the same from the time it's designed to the time it's bulldozed into the ground, that usually doesn't happen. And building usage constantly changes. Look at hospitals. hospitals change the usage for building every 5 or 6 years. Okay. Now, one of the downsides to manual balancing valves is, as we have a variable speed system and a variable flow system, our differential pressures are changing. So the problem with that is as we get that variable flow going on in the system, that means that the variable pressure is changing. So the balance valve becomes less effective at doing, the manual balance valve becomes less effective at doing its job. Now, if we couple that with a PIC-V, now we can have the manual balance valve and the PIC-V doing the job together to maintain the flow across the entire flow range and not adding excess pressure drop. Okay, so that's the whole idea there. If I look at dynamic balancing, and this is what you're doing when you put flow limiters in, and flow limiters are what's known as dynamic balancing. ASHRAE says systems shall be proportionately balanced, not dynamically balanced. So when we understand that, the theory behind flow limiters is that, well, if we put flow limiters in everywhere, doesn't make any difference because they respond to changes in differential pressure and they don't require balancing. You put them in for every coil, every air handler, every terminal unit, and you get the design flow everywhere. Well, the problem is they have a higher pressure loss. So inherently, as soon as I put that in, now I've got a higher pressure loss at each individual coil or each individual emitter. That higher pressure loss equates to pump energy. So now I'm using more pump energy to deliver the same heat transfer. Okay, they've got a higher cost. These things, because of the way they're made, they have a higher cost component. They're more expensive. They create certain redundancies at part load. One of the biggest challenges I found to them, and in my years working for a design firm, we use these things all the time because when they first came out, we thought they were great. And what we found is because of the small orifices that are inside there, and if you look, that's a very small orifice there that the water's actually got to go through. So the problem with that is that orifice, if there's any dirt in that system at all, and let's be realistic, it's a hydronic system, yeah, it may be clean when it's first started up, but if somebody doesn't maintain the water treatment and you start getting rust and sediment and everything else built up in the system, you can plug that orifice up. Well, guess what? If you plug the orifice up, now you don't get the right flow through it anymore, or any flow at all, for that matter. Understand that ASHRAE 90.1 says, thou shalt proportionally balance. This is dynamic balancing, not proportional balancing, okay? So if I use pressure independent valves, okay, yes, they work really, really well. However,
hey, sorry, Tony.
Yes, sir.
Robert says, but they're set and forget, right? I think he was talking about the other ones.
Yes, and so the downs, yes, they're set and forget. The problem is they are set and forget. They're set for a certain flow rate. If the building use changes, if the load on an air handler changes and you need to get more flow, you have to change out either the cartridge or the entire valve, depending on the style and the manufacturer. You may have to change out the cartridge to get a higher flow rate, even though your coil can handle it. So while they're set and forget, they're not great as the building needs change. Hopefully that answered that question.
Yep, I'm sure it did.
So if I look at pressure independent control valves, and I'm not saying the pressure independent control valves are a bad thing. Okay, please don't take what I'm saying about flow limiters or pressure independent valves as being bad. You have to understand what your design intent is and what you're really trying to do. Now, pressure independent control valves, they're easy to select. It's usually up to the controls contractor to select them. They work in on-off or modulating control. Yes, they can have some benefits to overall comfort. However, they're more expensive than a conventional control valve. And they increase your pump head. Not a lot, but they add increased pump head to it. Also, it takes somebody to go through and understand the variability and differential pressure in the system to set that valve up to work properly over the entire system operating range. It is not simple, and it's not a once and done. It takes multiple passes to go through the system and get it correct, and understand this is still a dynamic balancing methodology that does not meet the intent of ASHRAE 90.1. ASHRAE 90.1, again, says proportionally balance the system, okay? There was an article that came out in 2020 in the ASHRAE journal, and this particular author specifically says he doesn't want to use PICVs or pressure or flow limiting devices, and he prefers manual balancing because of the fact that there are so many variables in the system, and you're adding unnecessary pressure drop. You're creating issues with debris plugging and all this other stuff. And his recommendation is that you use manual balancing valves and only use pressure independent valves or PICVs when you are in certain areas of the building where you have higher differential pressure, i.e. closer to the mechanical room where the pumps are located at, okay? And that's where you want to, anything beyond that, most buildings out there will operate just fine and dandy with manual balance valves and conventional pressure dependent control valves. And you don't have to have the additional expense of PICCVs and flow limiters. So this was in the January 2020 ASHRAE journal. So if you want to go back and read the entire article, it was actually a really good article, but I had to steal this because it was just, it's so timely to what we're talking about today. So if I look at this, what are all the components that go into flow control? Well, I've got my control valve, which is controlling how much water is going through a coil at any one point in time in response to load changes. I've got my balance valve, and then I've got my variable speed pump. And with my variable speed pump, if I really want to minimize outside influence of things that can cause my pump to not control correctly, I want to utilize self-sensing pumps and not rely on the building automation system to tell that pump what speed to run at, but actually know that what my design flow and design head is, and allow my pump to control using the affinity laws and using the intelligence built into the drive to cause that drive to run and maintain the required flow rate regardless of what's going on in the system at any point in time. And if you want to have a deeper dive discussion about self-sensing and how that all works, reach out to Brett or I, and we're more than happy, or your local TACO rep, and we're more than happy to talk more in depth about how self-sensing really works. So what is circuit balancing? I promised we were going to talk a little bit about what circuit balancing is and where we're headed with all this. So if I look at a typical P&I diagram for an HVAC system, okay? And I don't show the pump on here, but for sake of argument, assume there's a pump in here. So if I start out, circuit balancing is an iterative process, okay? It's not a one pass through the building and you're done. And if any test and balance contractor tries to tell you that, oh yeah, I can balance it one shot and go through it and I'm done, he's lying to you. Or you're not going to get a quality balance, I promise you. I've been doing this almost 50 years and I have yet to see a balance contractor be able to go through a building one time and get it right. It's just not that great. Okay, so when I look at my design and I look at what's actually going on in the building, okay, what I have to understand is my goal is of balancing is to proportionally distribute the water flow evenly amongst all the coils so that I get the right flow at the right time through each individual emitter, and I'm balancing that pressure drop across all of the emitters so that I'm trying to create equal pressure drop, okay? And yes, I know this is shown with three-way valves, but it doesn't make any difference whether I have three-way or two-way valves. I'm doing the same thing, okay? So when I'm going to start out, I'm going to look at this, and so in this particular case, my most remote load, I've only got 95% of my design flow. Well, that's not going to get me where I want to be. So I'm going to continue on and I'm going to look at the next unit, and I'm still only at 95%. And now I look at the third unit, I'm at 95%, and that entire branch is at 95%. Well, what's that tell me is that my floor below, or my zone before that, is overflowing. I'm getting too much water in this zone down here. There's too much water down here, and not enough is getting up here to my most remote load. So what I'm going to do is, now as I check that, I'm finding out, okay, I'm at 105% there, I'm 107% in the middle, and I'm at 109% there. So you notice as I'm getting closer and closer to my mains, my flow is coming up. So now what I'm going to do is I'm going to go through the entire system. I'm going to get that branch reduced down to 105%, and start to bring the other two, get the branches to come up. So this is why I say it's an iterative process. You're going to slowly manipulate one part of the building to get another part of the building to come up to where it's supposed to be. Okay, so now once I've got my branches reasonably close to proportioned out so that they're about the same, now I'm going to come down here to the complete system level balancing valve, and I'm going to adjust it to get the total balance every place that I want it to be. Now, mind you, I'm doing this in zones. I'm not doing this at the pump. Okay, so when I'm doing this, I've got my pump set at design maximum flow and design maximum speed. And then I'm going out and distributing the water correctly out in the building. One of the mistakes that I often see young test and balance guys do is they try to set the flow at the pump first. Well, if you're doing that, you're not providing the full system head and the full system flow out to the building. You're retarding the pump. Years ago, we used to put MPVs in. We put multi-purpose valves in, or some people may call them triple duty valves, and we'd add a whole bunch of head at the pump to get the pump to come back on its curve. We don't want to do that today. We have a variable speed drive. So what we want to do is run the pump up to its design maximum speed, figure out what's the water's doing out in the building, and then work our way back to the pump and make the final trim at the pump. And we may have to reduce the speed a little bit. We may actually have to increase the speed a little bit, depending on what the total system head is versus what the actual design head is. Okay. So now at the end, we finally got this system. We have everything balanced to 100%. We've got everything doing exactly what it's supposed to do. And now we're going to make one final pass through the building to make sure everything is doing exactly what it's supposed to do. And generally speaking, it takes at least 3 passes to go through a building. I've had some buildings I've had to go through 4, maybe 5 times because something changed, or I found a problem as I was going through the system. And it's really all about understanding what changes you're making and where your goals are. Okay. I've had balance reports come in across my desk when I was working as a consulting engineer that everything magically matched my design details perfectly. Now, I consider myself to be a pretty good designer. I'm not that good, folks. I hate to say it, but in all my years of designing, I've never gotten a system to hit exactly perfectly what my design flows were supposed to be on my balance reports. I try to get, I'm happy when I get within 5%. Most of the time I'll accept 10%. But if I get a balance report that comes in that everything matches my drawings exactly, it really causes me to question how good of a job they did balancing that system. And usually the coffee stains and donut stains on the jelly donut stains on the balance report are my giveaway. Anyway, so to sum all this up, what we're really trying to do is we want to assure proper water flow to all of our emitters in the system. We're going to do this and minimize pressure drop. We want to minimize the excess pressure drop, because excess pressure drop equals more pump energy, and we don't want to increase pump energy. We want to keep the pump energy as low as we possibly can. By properly balancing a system, we reduce the risk of overpumping the system. And self-sensing is a great tool to help do that, but you have to understand the system and understand where self-sensing makes sense and where it doesn't make sense. And then the other thing is we want to identify issues. And I don't know what, all of you out there, if you're design engineers, if you're contractors, if you're, where you're at in the spectrum, I really like the test and balance guy to work for the design engineer rather than the mechanical contractor. And the reason I say that is that the test and balance contractor and the mechanical design engineer can work hand in hand so that the test and balance guy really understands what the design intent is. And that way, the engineer can rest assured that the system was actually installed and is performing and operating per his design intent. So that's my 2 cents on the design world.
Hey, Tony,
Anyway.
go
Yes,
back
sir.
go back to the drawing on the previous page, or one. Let's see the diagram. Let's see where the
That one?
diagram. Yeah. So Daniel's saying the diagram shows three-way valves.
Yes.
Excuse me. The diagram shows three-way valve systems. Is the process the same for two-way valve systems?
Yep, exactly same process. The difference is that, so I have to understand connected load versus pump capacity. And in a lot of buildings today, we take diversity, and schools are a perfect example. We know that we design the building for 100% capacity, but we also know that all the air handlers don't peak at the same time because the building layout, solar gains, people, all that kind of neat stuff. So we may have taken diversity in our design. So let's say we have, if I add up all my coil loads, I need 1,000 GPM, but my pump may only be sized for 900 GPM. So I'm at 90%. So I've got 10% diversity in there. What I have to do when I do that system is I have to understand where my most hydraulically remote load is, and then have enough valves open that I can achieve that 900 GPM, because I know I don't have enough pump that can handle 1,000 GPM. So you have to understand diversity versus connected load, and not all buildings have diversity. Okay, when I do hospitals, I have zero diversity. I assume 100% load all the time. Data centers, anything mission critical, I assume I got to have 100% flow all the time under a design condition. So you have to understand whether there's diversity in that equation.
All right, so let's see if we can get the question with this paragraph I'm going to read you. Usually, the chilled water demand at buildings terminals is more than the max pump capacity, because diversity factor. Therefore, the pump max capacity is 80% of total chilled water demand. So the main valves will not pass the max. They should on real life. Does that make any sense to you?
Yes, that was kind of what I was just talking about.
I think so, right? Yeah, right.
In understanding diversity. And it's up to, and this is why I say that the test and balance contractor really needs to work for the engineer and not for the mechanical contractor. So the test and balance contractor should be setting up a meeting with the engineer, whether it works for him or not, to have a discussion to understand the diversity factor taken into that building, because it depends entirely on the building type and what the critical components are. If I'm designing a hospital, hospitals, I typically don't take diversity. I'm designing my plant to do 100% of connected load, because hospitals have different loads. They have more of their loads are internal than external. But if I'm designing a school building, I've got internal loads, I've got solar loads, I've got, outside air conditions, all that. But I also know that in a school building, all the classrooms aren't necessarily in use at the same time. We've accounted for a gymnasium, an auditorium, a cafeteria. Well, if the kids are all in the cafeteria at lunch, that means they're not in the classroom. So the load's not in the classrooms, it's over in the cafeteria. So you can take advantage of that diversity and downsize the pump to match where to provide the load based on where it's going. But you have to understand that at time of balancing, so you understand how you're distributing the water and getting things so that it behaves the same regardless of where the load is occurring in the building.
Excellent. So from Alberto, so you balance each load to the design flow. What happens at part load? Is the balancing valve's behavior proportional to the reduced part load flow?
Yes, because pressure drop is proportional to the flow rate. Okay, so as we reduce the flow rate, as the control valve is throttling down, what we're going to find is that as we start to throttle the control valves down, the pump starts to slow down, and system differential pressure is going to change. And as system differential pressure starts to drop, that proportion remains the same across the balance valve. Now, it's not perfect. It's going to vary a little bit, but it's not going to vary enough to dramatically alter the balance. And the thing we have to understand with this is that in some systems, when you don't put your let's say you're not doing self-sensing and you're going to use a differential pressure transmitter to control the pumps. One of the biggest mistakes I see happen is the differential pressure transmitter gets placed too close to the mechanical room. And we don't get it at the most remote load. We as engineers, we design the piping system. We know what particular emitter was our index zone for our head loss calculations. That's where that differential pressure transmitter needs to be. Because if I can satisfy that load, all the rest of them will follow. And so what happens a lot of times is the DP transmitter gets placed in the wrong spot. And so we arbitrarily have to set the differential pressure transmitter or differential pressure set point higher than what it needs to be. So we end up over pumping the system. And this is why it's really a concerted effort between the engineer, the balance contractor, and even the controls contractor to get things set up correctly and pay attention to all the fine points of design.
So here's a great statement. Three-way valves should be used at the furthest coil on each branch to ensure flow through the entire system. Kind of a small bypass, right? I think.
Yeah, and what we have to understand is, as we've moved to variable primary systems or all variable systems, everybody's got to realize a pump's got a minimum flow. I can't deadhead the pump. So if I have 100% two-way valves in the system, where's that water going to go? Because the pump's still down there turning, it's still trying to move water. So I have to have some three-way valves out in the system. And I like having them at the far end of the system because that means I've got cold water everywhere or hot water everywhere. And any loads between the pump and that most remote load, if they start to call for heating or cooling, they'll get hot or cold water right away. If the three-way valve's all the way back at the mechanical room, you may have a whole long pipe run that is gotten warmer or cooler. And so there's a lag time between the time that valve starts to open and the emitter actually can do its job and do it effectively.
So great question from David. I hear this conversation a lot. What are your thoughts on the balancing valve on the supply or return side?
Balancing valve always has to be on the return side. Just like the control valve, it goes on the return side, on the leaving side of the coils. Because here's the problem. If I put the balancing valve or the control valve on the water entering side of that coil, that is, especially the control valve, we are reducing the flow rate going through that coil, and you have the potential, because you have to understand how a coil is built, okay? We don't have a single serpentine loop going through that coil. All the tubes in the coil are on a header. And so as I reduce the flow rate going into that coil, I can create laminar flow in the coil. And laminar flow is not good for heat transfer. So by putting the valves on the leaving side of the coil, I'm keeping that coil pressurized and I'm minimizing the potential for laminar flow at low loads.
So Henry's saying, great point regarding the balancer working for the engineer rather than the mechanical contractor. Now, if we could only get the CMs to buy out the job that way. Good luck.
I can't fix that problem.
I don't think many of us can. All right, here's a pretty long paragraph, but I think it's very important that we at least bring it up here. New energy codes, such as Seattle's and Washington's, are requiring PIC valves, PIC valves, to be used on all coils with flows above 5 GPM. However, this presentation says PIC valves do not meet ASHRAE 90.1, as they are not proportionally balanced. Is it fair to say that these new energy codes are mistaken in assuming PIC valves are the best methods for achieving optimal energy efficiency?
Well, boy, that's a loaded question.
Yeah, it sure is.
Here's the reality, okay? The best system design that I have found so far is a combination of PIC Vs and proportional balancing valves. And the reality to system design is that if we understand hydronics design and understand head loss calculations, we all do head loss calculations. And if we're not counting fittings, okay, I'm old enough to remember doing hydronic design and counting fittings and doing an actual head loss calculation in millinches per foot. That's how old I am.
What do you mean? You don't do that anymore? I still do that.
Yeah, right, Brett. I know better. But Brett, you're like me. You're the same age I am. And that's how we learned how to do this.
Yep.
Way back when, in the dark ages. And so in today's world, we look at straight lengths of pipe and we take it times a fitting factor, usually 1.5, and that's our head loss. Well, the problem with that is how complex is your piping system? Is your piping system, does it warrant a 1.5 fitting factor, or should your fitting factor be 1.25 or 1.3? And then the other thing that happens is we put safety factor in. And I've seen engineers put safety factor on top of safety factor on top of safety factor. So they put safety factor in on the load calculation. They put safety factor in on all their coils. They put safety factor on their pumps. They put safety factor on the head that the pump's going to operate at. And before you know it, you've got this massive safety factor in the system. When in reality, and in all the years I've been teaching design, I teach engineers to design with zero safety factor. Before anybody starts throwing daggers at me, listen to what I'm about to say. Design your systems with zero safety factor. Take all the safety factor out of your load calculations and head loss calculations and everything. Design the system without it. Then go back in and surgically insert safety factor where it makes sense. Think about this. If I have a hospital and I have a front lobby in the hospital, does it really need safety factor? But I have surgical suites. Does it need safety factor? Oh yeah, you better believe I want safety factor on the surgical suites. But do I need safety factor on the lobby? Nah, I don't need 25% safety factor. I don't even need, maybe I need 2%. But if I put 25% safety factor on everything, now I've got way more capacity than what I ever need. And now the system's going to run at part load conditions even more of the time. I mean, the cold hard reality to design is that 90% of the time, HVAC systems operate at 60% or less of full capacity. We know HVAC is a part load system by nature. And the goal here is to design our systems intelligently and effectively to reduce energy consumption. The other thing that I see happen, and Brett, I don't know if you've seen this as much as I have, but engineers specify where to put the differential pressure transmitter when the BAS is going to control the pumps. And what I often see is, oh, put it 2/3 out the longest pipe run. Well, what's that? What's 2/3 the longest pipe run have to do with anything? We have an index zone that we designed our system to meet the head at that furthest point. Isn't that where we want the transmitter to get the lowest possible value? And so if I'm combining PIC Vs and manual balance valves, the PIC Vs can be set at the lowest possible differential pressure that they can work with. And so they can handle those minor differential pressure changes, but the balance valve is there to really set the flow rate. The problem is if you use a PIC-V and you set it up to handle this really high differential pressure, you're taking a really high pressure loss across that valve and you're wasting energy because you're having to overcome that valve. So it's really understanding, I know what the intent was, and the intent was to minimize energy consumption and make sure the system gets balanced correctly. But it really comes down to us as engineers doing our part at the front end and making sure we have the right details to get the system balanced correctly in the first place.
So here's a great comment, and I'm sure this has happened to other folks on the call, and maybe you as well, Tony. We got a satisfactory test and balance report on a system, and the dampers to the zones were closed.
Gotta love coffee shop balancing reports.
Hey, he got his 18 holes in that afternoon.
Oh yeah, and you know the sad part is, Brett, I have seen that happen more times than not.
Yeah, that's sad.
I've had balance reports come in and it says that the pump speed's correct, got the design flow, got the design head, and I'm looking and I do the brake horsepower calculations and I'm going, how am I hitting design flow and design head at design speed, but my brake horsepower of the motor is half of what it should be by the pump curve? That can't happen. I know it can't happen. Mathematically, it can't happen. And so it's up to us as engineers, because last time I checked, the customer paid us to be the smart guy in the room, to look at that report and go, no, I don't buy it, reject it, send it back, try it again. Here's all the things that are wrong with it.
I tell you, you should read all the funny stories people have had out there. I've had fans balance out perfectly with no power.
Oh yeah, in my career, Brett, I have seen so many things that just wow. I shake my head, and there are days I've gone home to my wife and said, "Dear, you won't believe what I saw today," and she goes, "I thought you've seen everything," and I go, "No, not again."
So here's a great question: how often should a system be balanced? Is that even code? That's a great.
Well, it depends. It depends. It is. So what I tell people is, it should be rebalanced. Okay. So if I look at healthcare, and if I look at the healthcare guidelines says that before you make any modifications to a system, you go through and rebalance the system. Not necessarily rebalance, but verify what all your flows are, what all your head losses are, verify everything. So you know how the system is performing before you modify it. And that's a code requirement in the JCO and hospital accreditation code in the US, and I'm guessing it probably is in Canada as well. The other thing to understand is that should be applied to any building that we're going to go in and touch. Okay, we don't necessarily know, is the building really operating the way it's supposed to? As engineers, owner hires us to come in and do a remodel on a building. We assume that everything is working correctly. That's a dangerous thing to do, is assume.
I know what assume means. It's
yes,
got a lot of meanings.
Oh yes, it does. And it's going to get somebody in trouble. And you know, as engineers, we want to hire that balancing contractor to go in and verify everything up front. Let's see how it's working right now. So when we go and change it, we know what changes are really going to impact the system.
Here's a great question, and this comes up almost every time we talk pumps in classes. Do you still trim impellers on pumps with VFDs? We like to order pumps with an untrimmed impeller and enough motor and VFD to make it non-overloading, and use the VFD to trim pump speeds. Thoughts? That could get expensive. I tell you what, that could be its own class. That could be its own presentation for at least a half hour.
Oh yeah. I mean, the reality is, why would you do that?
It depends where you are on the pump curve. You know what I mean? Yeah. I always try to tell, or the family of curves. Like if you're in the middle of the if you got an impeller that's max at 12 and min at 8, and you're at 10 with your thing, with your design point, man, you don't want to go up. Your motor's going to get too big and expensive, and it's not worth it, you know. But if you're close to the top,
yeah, I mean, if I have a choice and I'm at, you know, I'm close to that max horsepower that for that particular motor, yeah, okay, and not a big deal. But
right.
like you said, if I'm in the middle of the curve, and if I go to full size, full trim impeller, and I have to go from a 30 horsepower motor to a 75 horsepower motor, that is a huge jump in cost. That is a huge jump in size, the weight. I mean, 75 horsepower motors by themselves, I'm not moving one. Brett, you and I aren't moving one together.
Nope.
I don't know that either one of us would want to move a 30 horsepower motor together, but that's a whole nother discussion. You know, and so if I go to a 75 horsepower motor, my drive just got significantly more expensive. My wiring costs just went up. So yeah, I get, okay, yeah, I want to make it non-overloading, but why would I want to do that? Why would I want to throw all that extra cost on the job? It doesn't make sense. And then if I do say, okay, well, I'm going to trim the impeller down. Well, why would I do that? I've spent more money on top of more money on top of more money. Just select it right to begin with.
So, and Henry's probably making probably a good point. That if you do that, you know, across the board, max impeller, max impeller and max motor size, that likely won't pass the 90.1 test due to excessive horsepower. That's a possibility as well, you know.
Yeah, because of the required energy reduction at 50% flow.
And Bill's this is a great one. Many times I go back to a system 2 years after test and balance, and the pumps are in hand. The operator has the system running wide open, so he doesn't get complaints. How true is that? You know, how true is
that? You know, as long as I've been in this industry, Brett, and I'm sure you've seen the same thing, as you walk back into buildings that you know were working correctly at one point in time.
Yep.
And God love the maintenance guys, but some days they do things because they don't really understand what they're doing. I had a job years ago. The maintenance guy opened all the manual balance valves wide open because he had no idea what they were doing, and destroyed the delta T on the system. And he was running the boilers so hard. These were Brian Flex tube boilers, and on a 30-degree day, the boiler, the firebox on the boiler was glowing bright red because the flow rate was so great going through the boiler. The thing couldn't meet delta T. It was horrible. I tried to explain it to him, and I was told that he knew more about HVAC than I did, and I went, okay, I'm done. I'm just not going to go there.
And then, I mean, there's a lot of other stuff, but we're getting near the end here. You want to, if we didn't get to your questions, we'll try to get to them offline. But Tony, great job. You want to say goodbye to everybody before I sign off?
Yeah, thanks everybody for your time and attention today. Hopefully you found this useful. If you've got more questions, reach out to Brett or I or your local TACO rep, and we'll help you. You know, our goal is to help build better systems.
Very true, and you know, well said. That's the difference between genius and stupidity, is that stupidity has no limitations. We got a lot of great comments today. That we've got them going. We've got them going. You know, it is a subject that a lot of people have experience with, right? And unfortunately, not all of the experiences are as good as they should be. You know, so thank you everybody. Yep. Tony, great job. Thank you.
Thank you, everybody.
Folks, we're back on in a couple of weeks. So see you then. Take care, everybody. Goodbye.
See y'all.
Goodbye.